All right, ladies and gentlemen, this is going to be a relatively long video because when you're dealing with Bohr diagrams, there's a lot of stuff to be covered and there's a lot of vocabulary to be done. The first thing that you need to realize is where these come from. So these are squares from the periodic table. Now, on your periodic table, there is a legend, okay? So atomic number, symbol, atomic mass, name, right? So we're going to work our way through. The first thing that we're going to do is we are going to determine how many protons, neutrons, and electrons that there are for each of these elements, all right? So I'm just going to put that here, protons, neutrons, and electrons for each of these elements. All right, well, the first thing that you have to understand, of course, is that that is the atomic number, and the atomic number is, by definition, the number of protons. So the protons is going to be 4. Next thing that you need to understand is that this is the atomic mass, and that this, by definition, is the number of protons plus the number of neutrons. Now, this is the average atomic mass. That's why you have the decimal place, but you can just round it to the nearest whole number, in this case 9. So our number of neutrons is going to be the mass minus the protons, or 9 minus 4 is equal to 5. So we have 5 neutrons. Every element on the periodic table, unless you know differently, has a charge of 0. So since this has a charge of 0, charge, if you recall, is equal to the number of protons minus the number of electrons, because protons are positive, electrons are negative. If the charge is 0 and you know that you have 4 protons, then you must have 4 electrons. So there are 4 electrons. Now we're going to do the same thing for each of the others, just to prepare the way for the Bohr diagrams to follow. All right, so here we go. I'm going to change colors to make it a little easier to see. So protons, neutrons, electrons. Protons is 7. Neutrons is 14, which is the mass number, minus 7, which is the atomic number. So neutrons is actually 7 as well. And since the charge is 0, and charge is protons minus electrons, a 0 charge, 7 protons must mean 7 electrons. Then we do the same thing for silicon down here. Again, change the colors. Protons, neutrons, electrons. So protons going to be 14. Neutrons is going to be 28 minus 14. Which of course is going to be 14. And electrons, because the charge is 0, the protons are 14, the electrons must also be 14. There we go. Now, that gets us our general numbers of subatomic particles, which we can move forward with from there. All right, now, ever since Rutherford did his thing, we've known that every atom is made up of a nucleus, and the nucleus has protons and neutrons. So the protons for beryllium is going to be 4. The neutrons for beryllium is going to be 5. And there is my nucleus. We can do the same thing for each of the others. We'll do them when we get to them. After that, we have the Bohr diagram. Is the electrons are in orbits around the nucleus. So these orbits have a series of rules that are associated with them. The rules for filling the orbits are these. You have energy levels, and you have maximum number of electrons. And so for energy level 1, the maximum number of electrons is 2. For energy level 2, the maximum number of electrons is 8. And for energy level 3, the maximum number of electrons is 8. Now, I will point this out over and over again, but let's try that again. Maximum number of electrons is 2 in energy level 1. Notice there are 2 elements in the first period. Maximum number of electrons is 8 in energy level 2. Notice there are 8 elements in the second period. Energy level maximum number of electrons is 8 in energy level 3. Notice that there are 8 elements in the third period. Okay, none of those are coincidental. All right, so we have a total of 4 electrons for beryllium, so therefore we need to put the first, actually I want that to be black. We put the first 2 into the first orbit. So 1, 2 electrons in the first orbit. We have some vocabulary, actually let's get the vocabulary at the end. Then we still have, we put in 2, we need to put in a total of 4. So we still have 2 more that need to go in. We put those in a specific way. We put 1 in. I hate it when it does that. We put 1 in there, and then we put the next in here. Okay? We do not pair them up. We do not pair them up. Now it's time to get some of the vocabulary in here so that you can refer back to it and know exactly what it is we're talking about. All right, so reminder, this of course is the nucleus, which is always protons and electrons. Oh, did I say that? Protons and neutrons. All right, this is energy level 1. This is energy level 2. This is referred to as a pair of electrons, an electron pair. Electrons that are not paired are referred to as lone electrons. Now, on the lone electron thing, we'll get more into this later as time goes by, but notice that you put them in singly, right? And the rule for that, there is a rule for that. It's called Hund's rule. We'll talk about it in greater detail later. But basically, Hund's rule boils down to electrons go in singly, until forced to pair. All right, so that's pretty much everything that there is to show with regards to beryllium. Now, when we move on to nitrogen, again, we're going to do the same thing over again. So nitrogen, we've got 7 protons, we've got 7 neutrons. That is our nucleus. When we start to put the electrons in, we're going to put the first 2 of the 7 into the first orbital, or into the first orbit. They are going to be paired up because you can't put any more than 2 in there, so they must be paired. That leaves us 5 left to do. So we put in the second energy level, and then we put in our 5 electrons. Now this is where Hund's rule comes into play. We put our first one on the north side, our second on the east, third on the south, fourth on the west. We still need to put in one more, so we pair them up singly until forced to pair. So nitrogen is always going to have 1 pair and 3 lone electrons. Now, it's about time to start looking at some patterns on the periodic table so that we can then apply them to the next one. Notice that on the outside shell, that outside shell is called the valence shell. The outside shell. Notice that there are 2, 3, 4, 5 valence electrons in nitrogen. Notice that nitrogen is in group 5. That is not a coincidence. Let's see if that works on the other one. On the first one that we did, beryllium, the valence shell had 1, 2 electrons in it. If we find beryllium, we'll see that beryllium is in group 2. So what this is telling us is that these group numbers, 1, 2, 3, 4, 5, 6, 7, 8, those group numbers are the number of valence electrons. Now, there is another pattern here that we can look at before we get to silicon and we pull the whole thing together. Notice that there are 1, 2 energy levels here and 1, 2 energy levels here. And notice that both of these elements are in period number 2. So, your period number is the number of energy levels. Now, if all of that is correct, then it should match up with silicon, okay? So silicon, we can see silicon is right here. It is in group 4 and it is in period 3. So we should end up with 3 energy levels and 4 electrons in the valence shell. So I'm going to go ahead and write that down because that is our prediction. We should end up with 3 energy levels and 4 valence electrons. Now, I'm going to put a little box around that just to draw our attention back to it when we're finished. And let's do our Bohr diagram, Bohr model, and see if we're right. Okay, so the protons are 14. The neutrons are 14. And we have 14 electrons to put in there. So the first set is going to go in the first energy level, a total of 2. And they're paired because you can only have 2 in the first energy level, so they have to be paired. The second energy level, not very good at drawing circles, but the second energy level has a maximum of 8 because there are 8 elements in the second period. Put them in singly until forced paired. Hund's rule. 1, 2, 3, 4, 5, 6, 7, 8. Now we have a total of 10 electrons here, which puts us right about there at neon. We still have 4 more to go. So we put in our last orbit, our third energy level. We have 4 more electrons to go in there. 1, 2, 3, 4. So let's check our predictions. 3 energy levels. 1, 2, 3. Yes. 4 valence electrons. 1, 2, 3, 4. Yes. So everything that we predicted has come to pass, and that is, in fact, the Bohr model or Bohr diagram for silicon.